Welcome all. This is Dr. CVR Padmaja, Associate Professor, Department of CSE, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss binary search technique, working principle and implementation. Binary search. Before discussing binary search, let us try to get the definition for search. Search is a utility that enables its users to find documents, files, media, or any other type of data held inside a database. So, search can be considered as a utility program. Okay, search works on the simple principle of matching the criteria with the records and displaying it to the user. If we find the required data, the process of searching is considered as a successful, otherwise unsuccessful search. Binary search algorithm works on the idea of neglecting or reducing half of the list on every iteration. It keeps on splitting the list until it finds the value it is looking for in a given list. Binary search is commonly known as half interval search or a logarithmic search. Sometimes it is also known as prune and search algorithm. It is a best example for prune and search algorithm. What do you mean by prune? The word prune means to reduce something by removing things that are not necessary. Prune and search is an excellent algorithm paradigm for solving various optimization problems. This approach consists of several iterations. At each iteration, it discards a fraction, say f, of the input data and then invokes the same algorithm recursively on the remaining data to solve the problem. So, binary search working principle. How the binary search works. So, there are various steps. We will try to understand each and every step here. The first one is compare the key with the middle element. Take a list of elements. To implement binary search, we need to consider some list. So, let us take a list here, and in the list, take the middle element and try to compare the middle element with the key. If that middle element matches the key element, then return the index of that middle element. Otherwise, you check whether the given key element is greater than the middle element or else less than the middle element. If x is greater than the middle element, then x lies on the right hand sub-array, on the right hand side of the sub-array after the middle element. So we recurve for the right half. That means we will search for the key element in the right hand side of the list, discarding the left side. If x is smaller than the middle element, then we will recur for the left half by discarding right half. This is how we will repeat this process till we find the key element. Otherwise, we exhaust the list by getting low is greater than high. So, we basically ignore half of the element just after one comparison. This is really boosts up the timing complexity. It reduces the timing complexity so that it can be applied on any sorted list or sorted elements, so that it increases the efficiency of the algorithm. The working principle example. Now let us take a list of elements. Here we are having a list of 6 elements: 15, 25, 35, 45, 55 and 65. And the key element is 55, that which we want to search here. So to search this particular element, we have to traverse the list. In linear search, we'll try to compare the key element with the first element. If it is not a match, then we will go with the second element, and then third and fourth, like that. But coming to binary search, we are going to consider two elements or two data. One is low and the other one is high. Low is nothing but the index of the first element, and high is nothing but the index of the last element. So in our case, low is equivalent to 0 and high is equivalent to 5. And we will try to get the middle point of the list. So by calculating, mid is equivalent to low plus high by 2. Here low is 0 and high is 5. So 0 plus 5 by 2, which returns 2. Exactly it is 2.5, but we will go with only integer division, so we will get 2. So at index 2, we are having the middle element, because here the size is an even number. If it is an odd number, then we will get the exact middle point. But here, because the size is even, we will get either first one or the second one in the middle two elements. Generally the first one, because we are going with the integer division. So after getting the middle point, that is 2 here, after getting the midpoint 2, we will compare our key element with the middle index value. Suppose the name of the list is A, then we will compare with A of 2. We'll compare key with A of 2. So what is A of 2? That is 35. Is 35 is equivalent to 55? No. Then we will go with the second part. What it is? Here, the key element is not equivalent to A of mid. It is not equivalent. So the key element can be greater than the middle element or less than the middle element. Next, we have to check whether key element is greater than A of mid or not. So here in our case, key element is greater than A of mid. So what we have to do? This is middle element. So our key element is more than the A of mid. So we have to check for that key element in the second half, that is on the right hand side. We have to discard the left hand side list. So for that, we are going to change the values for these things, low and high values. We will adjust low and high values. But especially in this case, we will adjust only the lower value. So here low will become mid plus 1. It will be mid plus 1. So what does it mean? Now A of low will be, low is equivalent to mid plus 1. That is nothing but mid is 2 plus 1, 3. Low will become 3 now. Low will become 3 now. So next time when we are going with the next iteration, when we are calculating the middle value, now the low value is 3 and high value is 5. Now this by 2, which is equivalent to 8 by 2, which is 4 now. Now we will compare our key element with A of 4, A of mid. Now the A of mid is this one. So we will compare A of mid with the key element. So here the key element is equivalent to the middle element. So the match found. The search is successful in this case. Now we will return that index 4, that mid value 4 as the location, as the index at which we found the key element. This 4 we have to return. Suppose we are checking for an element which is something like 42. We are checking for 42. Then what happens? Already we came to, this is our A of mid. This is our A of mid. So now instead of 55, now it is 42. So is 42 is equivalent to 55? No. So what we will do? Now we have to leave either RHS side or LHS side depending on the condition. Is 42 greater than 55? No. So now we are going to discard the right hand side and we will go with the left hand side. So only this portion we are going to search. Previously this portion is discarded. Okay. Now is 42 greater than 55? No. So now 42 is less than the key element. So we have to adjust these values. This time when we are adjusting, this time previously this is low and this is high. This time what we will do? We will change the high value, not the low value. Previously the low value is 3. Now the high value will be changed. So what is the high value now? High will be mid plus, high will be mid minus 1, which is equivalent to, previously the middle element is 4 minus 1, which is equivalent to 3. So here low is equivalent to high. Low is equivalent to high. So 3 plus 3, by next time when we are calculating next iteration, we will get the middle value as 3. Now we will compare this 45 with the key element, which is 42 now. So here it is not a match. So next we have to check whether 42 is greater than the middle element or less than the middle element. In this case, it is less than the middle element. Once again, we have to change the high value. Now high will become mid minus 1. That is this time 3 minus 1, which is equivalent to 2. So now the high value is, now high value is 2 and low value is high. Now this time your high value is less than the low value. So when we get high value is less than low value, then automatically we have to stop the search because we exhausted the list. Previously we searched up to this point. Now with the changes we searched till this point. So we exhausted the list. There we can stop the searching operation and we can announce that the element 42 is not present in the given list, which leads to an unsuccessful search. This is how we are going to implement. This is the idea. Next, we will try to write a code in Python language. We'll see that one also. Here, we are considering a list by taking A is equivalent to some list of numbers. And here, we want to find x is equivalent to 19. X is equivalent to 19. That is the element which we want to search in the given list. So, is 19 present here? No. So, we have to get that element is not found message. So, for that, we are calling the method binary search by passing the parameters array, the key element, the low value and the high value. Low is 0 and high is the length minus 1. That is the last index value. So, if here the control will be transferred to the function binary search and the result will be stored, the return value will be stored in the result. If that result is equivalent to minus 1, then we are going to display that the element is present at index or at location. If it is index, we will write the result. If it is location, we will write result plus 1. Otherwise, we will display simply not found message. So this is the driver code, and now we will try to write a definition for binary search method in the next slide. Here, in the binary search method, the arguments are array. The arguments are array, the key element, low and high value. Low is 0, and high is equivalent to length minus 1. How many elements we are having here? 7 elements. So, high is equivalent to 6. And what is the list? 25, 23, 45, 52. 60, 74, 82, 90. So, arbitrary numbers, any number we can take. So, now the low value, low is equivalent to 0 and high is equivalent to 6. These are the parameters we got from method, from function call. So, is low less than or equivalent to high? Yes. Yes. Then we will enter into the while loop. Now, in the while loop, what we are doing? We are calculating the middle element. Middle element is equivalent to low plus high by 2, or else you can use this formula also. So, what we are doing here? So, we are calculating the exact middle point. So, here 0 plus 6 by 2, that is nothing but 3. So, is array of mid is equivalent to x? What is array of mid? Array of 3. What is array of 3? It is 60. Is 60 is equivalent to the element x? What is x? X is equivalent to 19. Is it equivalent to 19? No. So, what we have to do? Next, we have to compare that whether the key element is greater than the middle element or less than the middle element. So, next we are checking is array of mid is less than the key element. If it is less than the key element, we are changing low value. Otherwise, we are changing high value. So, in our case, array element, the key element is less than the A of mid. So, what we are trying to do now? Previously, low is indicating here. This is our low and this is our high. Now, what happens? Low is equivalent to mid plus 1. So, here what we are doing is array of mid. What is array of mid? 60. Is it less than x? No. So, what we will do? We are going to change the high value. What is high now? High is equivalent, previously high is 6. Now, what it is? Now, how we what value we are going to assign for high? High is equivalent to mid minus 1. Mid is previously it is 3. So, 3 minus 1, which is equivalent to 2. So, this will become our high. It is no more our high. So, now that means what we are doing? We are discarding this part. We are searching for 19 in the left hand side. In the left hand side of the list. So, right hand side of the list we discarded. So, simply what we are doing here? We are taking the middle point of the list. We are comparing our key element with the middle element. If it is a match, we are displaying. Otherwise, basing on the value of the key element, whether it lies on its right hand side or on its left hand side, because the list is sorted here. So, that is the major advantage. If the list is not sorted, then we cannot do anything with the binary search. So, here because the list is ordered, we are discarding either of the sides. So, here now the low is 0 and high is 2. Next, we will go with the next iteration. Now, we will calculate the middle value for one more time. Now, the middle is equivalent to low plus high by 2. What is low? 0 plus what is high? 2 by 2, which is equivalent to 1. So we'll compare 43 with 9. Yeah, because middle is equivalent to 1, A of 1 is equivalent to 43. So we'll compare A of mid with our key element x, 19. 43 with 19. Is it a match? No. So what we will do? Again we have to go any of these two conditions. Here also our key element 19 is less than 43. So that means array of mid is greater than the key element. Then also we'll reduce the high value only. High will become mid minus 1. That means high will become 0. So next time high will be 0. Previously high is 1. Now both low and high represent the same. That means this is the location. So here once again we will check. We will go to the next iteration and we'll try to calculate the middle element. Both are zeros, 0 plus 0. So it returns the middle element also as a 0 because of this 0 divided by 0. Because we are starting from the first index, we are changing the formula slightly like this. You can evaluate this one on your own. Okay, so here we are going to check our key element with the first element. Key element is 19 and 19 compared with 25. So again it is not a match. So once again it will try to reduce because here also the A of mid is greater than the key element. It will try to reduce high value only. So high value will become minus 1 which is less than the low value. So automatically we exhaust the while loop because here high becomes less than low value. At that position, we will exhaust the while loop and this function returns minus 1 because 19 is not present in the list. So next one is time and space complexities for binary search. Here the space complexity is 1 and the time complexity for binary search algorithm is order of log n. So how we are getting this one? Actually check to check whether an element is present in the given list or not, in a given list of size n, the time taken to search an element in a given list of size n is equivalent to the time taken to search an element in the half of the list plus some constant time to calculate the middle value and all. So this is nothing but this is equivalent to n by 4, again half, again some constant time and so on t of 1. That means when the size is equivalent to 1 plus some constant which is equivalent to some constant. This t of 1 is also some constant time. So if we add up all these things, recurrence relations, if we add up all these things, then the timing complexity for binary search algorithm is nothing but log n. So in computer's notation, we will represent that one as order of log n. The timing complexity for binary search is order of log n. And the space complexity is 1. The applications of binary search. The applications of binary search, it is not linear search. The applications of binary search algorithms are libraries of Java, .NET, C++, STL, and so on. While debugging also, the binary search is used to point out the place where the error occurs. This can be implemented in compiler design, like when we are maintaining some log books and all. That can be elaborated when we are discussing other data structures also. This is how the binary search algorithm can be implemented. And coming to the prune and search algorithm, It is used extensively in optimizing problems. Binary search is an example for prudent search, and there are some other problems we can discuss on this particular technique in coming sessions. Thank you. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.